from the module. So design, I've kept it small and simple. 8 modules hang from cables from a central gyroscopic motor. Now these are essentially 9 moving parts, and they're going to be rotating as we would in a torus. I've kept it small, 20 meters across. This means that for a 10 centimeter long mouse, you've got that same 1% ratio between head and foot. 20 meters is something we can launch in spacecraft that are flying today. How does it work? Well, I've thought that sunlight can be reflected through windows into each module. So to better visualize that, we've got the sun behind the spacecraft, sun shines through the cables, and each of the modules only has windows on this side, so they're not exposed to direct sunlight. What we can have is either reflectors, filters on the solar array, so that we can filter out some of the worst radiation and reflect it back into the individual modules. Also, we want something that can not just stay at the distance from the sun that the Earth is. So having a solar array or a reflector array that can be planar or concave, so it can concentrate the light into the modules, or alternatively, as you get closer to the sun, be able to diffuse the light so that the plants and animals in the module receive the same amount of light as they would expect on Earth. Day-night cycle. Rather than using lights inside the module, since this is reflected light, I've suggested we have a solar fan array that rotates once every 24 hours relative to the rotation of the entire craft. So as you can see, you've got the dawn line is moving around slightly faster than the rotation of the craft itself, and that would mean that we can simulate a more natural day-night cycle inside the craft. I've used Falcon 9 as a rocket model just because I could get the details for the payload bay. These are rockets that have already been launched. You probably saw the launches last year. The payload bay is only 4.6 meters across, so I've designed my craft around there, and I'll put the caveat out there, I'm not an engineer, but I believe this is a feasible way of packing modules into the payload bay. You've got a central gyroscopic motor, 8 modules which are stacked on top of each other, so they can be launched in an upright position, so any of the plants and animals that are in there aren't being thrown around inside the craft. You have a solar fan array which is folded up on launch, and a folding truss structure which will be used to deploy the modules. So it's got an offset hinge. How this works is you've got this offset hinge, so as it deploys, half of the modules come out, the fan unfolds, and so now you have, this is the first action once it's in microgravity, you have a situation where the craft is balanced around the central gyroscopic motors. I'm not going to pretend that it's rotating, but if we pretend that it's now rotating, the modules feel a centripetal force to the outside, and if we have this truss that runs down alongside the modules, we can, like dealing cards from the bottom of a pack, we can individually deploy the modules, and they're counterbalanced, so the cables, which I haven't shown here, have to be bundled up, and that's something which would need to be designed carefully. But as the modules deploy, we can do this staged deployment, so eventually they find their place around and equally weighted around the central module. And as this can be done as the module is gradually speeding up, we have gyroscopes in the current space station which maintain attitude, and these by Newton's law would gradually speed up and achieve 1g of acceleration. So possible issues with design, heat management. As I understand it, the biggest problem with the space station as it is currently is not keeping it warm enough, but actually keeping it cold because it's bathed in straight sunlight. So is it possible, and I was speaking with Jim Shear, who is, I'll apologise for forgetting his title, but he's a missions organiser at NASA, was saying, yes, it is possible to have a passive module which has a gases on which surround the module, and as it receives sunlight on one side of the module, it radiates it on the other, so the entire the module can stay at a stable temperature. Obviously, I've designed this so it's not a solid torus. It's modules hanging out from a central motor, so there are various systems for deploying cables without them getting tangled up. Will we have resonance effects of the modules bouncing around? That might be a problem, but that would be a further something to look at in the further design. And also, you've got these long cables which are being exposed to solar radiation. There's a possible magnetic flux can be induced across the cables, so maybe we need to use different materials. And lastly, of course, if you use a solar panel which is not perpendicular to the sun, maybe you lose solar energy. Maybe there needs to be a different design of solar panels in that system. So I've said do 4 duplicate designs, 4 counterweighted designs so 4 designs of modules that are done in duplicate. I've said now these are just my ideas, but it would have to be further researched. Have a algae bioreactor relay which recycles and filters most of the air that goes through the system. Have mice which are planted in each end of the capsule, so perhaps you would put female mice in one end and male mice in the other end, so they don't find each other until later on once the system has been deployed. And then have a variable area in the middle which is modular, and we can change the environment from module to module. And you've got these 4 supplementary pillars around there which you would put your electrics and other things into. For the first one, of course, you want to test whether these mice do get sick after extended exposure to sterile conditions. So you have food and water supplied, have animal waste neutralized by an antiseptic floor covering, keep it as sterile as you possibly can, but maintain the activity of the mice with mazes and puzzles. A second type of module, which would be the first of 3 antigen stimulus configurations. So you've got plants, which are the single variety of plants which are edible. The mice can eat them as well as the food that they're provided. But also you've got a soil layer which helps to recycle the waste. You've got invertebrates, so bugs in the soil, fungi in the soil. That's one certain class of antigens that the mice could be exposed to. Have a second configuration where you've got a diverse set of plants. Have either flowering plants or other things which produce pollen, which are another class of antigens in there which produce different kinds of immune effects. Do these kind of immune responses that will generate in the mice, is this necessary in a space environment? And of course you've got the same bugs, fungi and microbes in the soil for waste processing. And lastly, have some kind of predation in there which produces a different kind of the mice will be scared or other different behavioral characteristics once they're in a situation where they have predators. Is that necessary for the completion of a complete ecosystem? So how do we measure the outcome of this? I'm trying to, obviously we can see the entire module be deployed, but how do we measure it? Well, we have a pad. Firstly, we can measure the weight of the mice. We can require the mice to stand on a simple measurement pad before food is allocated. train the first generation mice. If they know that's where food comes from, then it keeps coming. We can monitor through video feeds the litter sizes and survival rates as the colonies progress. At a certain point into the deployment of the module, so maybe 2 years after a number of generations of mice have gone by, we can expose the mice to a known pathogen. So C. rodentium is like, it's gastro for mice basically, but there are mouse flu or any number of other mouse pathogens which could be a good test, which wouldn't kill the mice, just let us get a measure of how healthy they are. And if a problem occurs, then we can euthanize them. But as a second mouse measure, we can make GM mouse, which will actually give us GFP it's a dye from a jellyfish, which we can put into mice, and we can use that to actually measure internally how healthy are they. Are their T cell counters up? Are they inflammatory? Do they have inflammation? And what we can do is have a green fluorescent protein that reports what are their levels of interferon, what are their levels of T cell activity, and by putting a UV light on them, we can measure that quantitatively by looking at the color on the thing. Okay, I'll hurry up. So lastly, getting towards the end, we put Carousel Space Station in a polar orbit so that Earthshine won't affect the day-night cycle. We need multiple video feeds, so we'll want to have a third rotational axis on the module so that it can communicate constantly with Earth, and we can monetize it if we want by producing some kind of reality TV show if there's a market for that. Why do this in space? Optimization of the design can be done on Earth, but there is this fifth challenge, the radiation environment of space. So we're only going to get real results for this if we do it in space. Also, we'll learn how to remotely manage an ecosystem in the context of a modular spacecraft, and it will also provide a model, a proof of concept that we can deploy a spacecraft that uses centripetal acceleration to generate gravity. So just to sum up, we want to answer the question if immune dysfunction will be problematic for long-term spaceflight. We have a modular design which allows us to deploy it by a single spacecraft that we can use now. We've got a mouse model which we know a lot about, and we can get detailed data on how healthy they are. And the multiple species mixes will basically, we can test if we can find a self-sufficient environment. Thank you very much.